Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for August 28th, 2013.
On today's show, an IR camera is a valuable tool for detecting whales in the wild, mechanical pressure is converted to light signals, and we meet the first winner of the Optical Society's Enabled by Optics contest.
An infrared camera has been turned into a tool for automatic whale detection on board the German research vessel Polarstern. It is designed to detect whales by their spouts during times of loud industrial noise. Regulatory authorities request mitigation measures for the protection of marine animals when in close proximity to loud activities, such as pile driving during wind farm construction or using air guns during oil and gas exploration. One such measure involves monitoring the surrounding seas and turning off the equipment when whales approach. That task, however, is easier said than done because spotting the spouts is quickly tiring for the eyes and concentration can be lost. Physicists at the Alfred Wegener Institute's Ocean Acoustics Lab have spent the last 4 years trying to find a way to continuously monitor the surrounding seas for whales. The answer was found in advancing Rheinmetall Defense Electronics' first Navy IR camera into a tool for automatic whale sightings. The thermal imaging camera is located 28 meters high in Polarstern's crow's nest. The thermal sensor is so sensitive that it detects differences in temperature of less than 1/100th of a degree Celsius. The whale spouts, which at least in subpolar and polar regions are significantly warmer than the sea surface, appear as light gray or white fountains. A whale spout is bright on the thermal image and then becomes darker again in a very specific pattern. Software developed at the Institute divides each of the recorded images into 31,600 little snippets, which are individually examined for brightness differences. The computer decides whether snippets exhibiting significant contrast change bear the characteristic features of a whale spout. That way they can also spot animals emerging for only a very short breath of air. Direct comparisons during one of the expeditions showed that the thermal imaging camera recorded twice as many whales near the vessel than did scientists using just binoculars. The strength of their system is that it can locate large whales, such as blue, fin, right, and gray whales around the clock, especially at night, with great accuracy, providing for better protection. Following the successful test of the technology and its ability to operate in inclement weather, they have now coupled a second normal camera to the infrared system that automatically shoots photos of each detected whale. This way they can not only collect valuable information on the size and distribution of populations of different whale species, but track individual whales and explore their behavior. The work appeared in PLOS One.
A new sensor device uses thousands of nanoscale wires to convert mechanical pressure into light signals that can be captured and processed optically. Developed at Georgia Tech, the sensor could be used in biological imaging and microelectromechanical systems. With the potential to provide an artificial sense of touch with sensitivity comparable to that of human skin, the device may provide a new approach for human-machine interfaces. Individual zinc oxide nanowires operate as tiny LEDs in the device, providing detailed information when placed under strain from mechanical pressure. Known as piezo-phototronics, the technology provides a new way to capture information about pressure at very high resolution, up to 6,300 dots per inch. Nanowires are compressed along their axial direction when pressure is applied to the device, creating a negative piezo potential, while uncompressed nanowires have no potential. Differences in the amount of pressure applied translate to differences in light emitted from the root, where the nanowires contact gallium nitride film. The ability to see all of the emitters simultaneously allows the device to provide a quick response. As the light emission is created, it can be detected immediately with the optical fiber, meaning 1 million pixels can be read in a microsecond. The research was published in Nature Photonics.
I recently spoke with Wes Fromm, Vice President of Engineering at Trojan Technologies. The company is the first winner of the Optical Society's Enabled by Optics contest. The contest aims to promote the extraordinary impact optics technology has played in making technological advances in our world and the critical role it plays in everyday life. Trojan has led the development of water treatment solutions using environmentally friendly ultraviolet light. Today, it has the largest installed base of UV systems in operation on the planet. Here's Wes to explain more about the company.
Trojan Technologies started in 1977 with the introduction of ultraviolet light being used ultimately to disinfect wastewater. And since wastewater, we've since moved into removing chemical contaminants as well as disinfecting drinking water. So it's all premised on using UV light and very specific frequencies of UV light, commonly known as UVC, so light in the range of 200 to 200 nanometers. And what happens is we can use that light for basically three purposes. The first and most common that we use UV light for is disinfection. And what happens is those high energy photons, typically around the 250 to 260 nanometer range, will impact on a microorganism, and they will destroy that organism's ability to reproduce, thus disinfecting the water. So in the design of a system like this, you'd use it probably in one of two places. First of all is in drinking water, so there's probably over 500,000 cottages, farms, small business establishments that have our UV systems in there that protect their drinking water. But UV light can also be used to disinfect wastewater, and that's the final step in treating wastewater before it's released back into the environment, is to remove or to disinfect all the pathogens that remain in the wastewater. So disinfection is the first thing that we do. UV light can also be used in photolysis, which is using UV to break down chemicals into their less harmful constituents. But more commonly for us, we do something called photooxidation, where we inject small amounts of hydrogen peroxide, use the UV to break the hydrogen peroxide into two hydroxyl radicals, and then those hydroxyl radicals tend to work on micropollutants that are in the water and reduce them to less harmful byproducts. Currently, we have around 8,000 municipal installations around the world. Most of those are wastewater, but many large cities have UV drinking water systems as well, for example, New York City. As well, we've calculated that approximately 1 billion people, or a few more every day, are touched by UV water treatment from Trojan Technologies.
Well, that really is a great green photonic solution. And you can learn more about it in a webinar from Photonics Media and OSA on September 11th with Wayne Lem of Trojan Technologies.
The contest also selected a winner in the student-produced video track, and we'll bring you that story next week.
Well, that's it for this edition of Light Matters, the photonics industry's only weekly newscast.
As always, you can write to us with your questions or comments at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.